I'm Mark Spencer. I'm a research physicist at the Directed Energy Directorate of AFRL. That's at Kirtland Air Force Base. Let me kind of give you an overview of directed energy, in particular a laser weapon system aspect of directed energy. So pictured here is an air-to-ground mission. And what we want to do is propagate a laser beam from point A, which is the laser source, to point B, a distant target. Okay, and there's many problems to solve along the way, but the benefits, why the juice is worth the squeeze, as we like to say, is the fact that direct laser weapon systems offer speed of light delivery. Nothing travels faster than the speed of light. Unparalleled precision. We have a laser beam. We can focus that laser beam to that distant target. And then the thought of we have a very deep magazine. So if we have a lot of incoming threats, we can engage those threats and take them out. Okay, so the things that I need to solve is the problem of how do you propagate the laser beam through the atmosphere and focus that energy tightly onto that target. And so there's things like aero-optics that we have to take into account, turbulence along the path, and also the heating of the air, which causes thermal blooming. All these physical mechanisms distort the light and cause the energy to spread. So the fact of the matter is we have what is known as a deep turbulence problem, distributed volume atmospheric aberrations. And if we can send out a second laser that engages with a target, then that light scattered from that target and that's received back at the tactical platform can be used to sense what those aberrations are. If we can sense, then we can correct, so we can compensate the outgoing high energy laser beam and obtain a lethal fluence on the target to take it out. So what we're trying to do is engage our extended non-cooperative targets and solve the deep turbulence problem. But this problem, what I'm calling the deep turbulence problem, is not only relevant to laser weapon systems, beam projection and compensation, but also to ISR, intelligence, surveillance, and reconnaissance. How do we do target ID at extended standoffs? So we want to fly our aircraft out of the combat zone and engage distant targets. They have to solve the deep turbulence problem as well. And then also optical communication. So you want to send light to a distant place and communicate with that distant place, but you got to get the photons there. If you don't get the photons there, then you can't do the communication. So one aspect of the problem that I'm working on is how do we characterize these atmospheric turbulence effects. So pictured here is some efforts that we're doing. This is Matt Benet. He's actually one of my SMART scholars that I'm currently mentoring. He's been spearheading these efforts. But what we do is we take a very simple telescope system with a camera on the back, and we're in the Lamberson Laser Research Facility here, imaging down looking. So we're about 9 stories high, down to a 1 and 2 kilometer site. So here's an imagery of a target board out in the distance. And what we do is the turbulence is distorting the imagery of that target board. And what we're plotting here at the top is kind of the magnitude of that turbulent effect. And what you see is throughout the day, temperature variations give rise to index of fraction variations, and we're plotting the magnitude of those index of fraction variations. So as things heat up, the turbulence gets strong, and as things start to equilibrate, the turbulence stops to play a role. And so now once we have this data, we can look at the bar chart here and say, okay, what is my 50% case? How strong is the turbulence 50% of the time? That's the green bar. But what if we're in the 90th percentile where it's really strong? That's the yellow bar. And then what if we're at 10% or 20%? That's the blue bar. So that gives at a system level the data we need to engineer solutions to this very hard problem.